Right, so this is the second unit within the Certified Ethical Hacker certification, and we're going to look at the technical foundations of hacking. So the main things that are covered in this presentation will be the OSI 7-layer model. We'll have a look at TCP/IP and Ethernet, and also looking at ARP. Have a look at the TCP packet structure, and especially around the TCP flags. And then we'll look at UDP and how it differs from TCP. An important concept within inside security is the concept of TCP ports, server ports, so we'll have a look at that, and then we'll look at ICMP. Okay, so the OSI model was created by the ISO, and its main focus was to try and standardize hardware and software so that it was possible to interconnect systems together. It also reduces the overall complexity as we can look at different layers of abstraction. For example, we can look at the network layer if we're interested about the routing of data packets across the internet. If we're interested in looking at the connections between computers, we might look at the Ethernet data link layer. If we're interested in the connections that are made between two computers, we might look at the transport layer, and so on. So it's really an abstract model that allows us to abstract the system into many different ways. And what happens is that we take data and then we add on a certain bit of data onto certain headers onto the data that will only be interpreted by the same layer on the other side. So the data goes through application, presentation, session, transport, network, data link, and physical, each adding their own little bit of information in the form of a header. And then on the other side, the data is then unencapsulated, and it goes through the basic layers again, each layer looking at the additional information that's been added which is relevant for that layer. So at the end we should end up with the data in the same form as it was meant to be transmitted. At the application layer we have typical application layer protocols such as Telnet, web browsers, and FTP and so on. Then below that we have the presentation layer, which looks at how the data will actually be presented. So this might be in the form of ASCII codes, EBCDIC, which are 8-bit equivalents of ASCII or ANSI formats. So here we can define how the text characters are going to be interpreted. Below this we have the session layer, and this is involved with controlling, creating and shutting down the TCP sessions that we actually create. So typical session layer protocols include our RPC and SQLnet with inside Oracle. The transport layer is then used to define the basic flow of data segments between the two computers. So it's within here that we get typical protocols such as TCP and UDP. This is normally the layer that's involved with reliability and actually creating a connection. So any errors within inside this layer are often highlighted. If we want a strictly connection orientated system, we use TCP. A connectionless system is UDP. Below this we have the network layer, typically defined as layers 3. And with this we get the concept of logical or network addresses. So these aren't real physical addresses, but they are organized in some way that allows us to route data between different internet networks. So here we get IP and IPX addresses. So this is the core layer of the internet, is the network layer. Okay, so below this we get the data link layer. So obviously we need to be able to transmit from our computer to the next device and so on. So the data link layer is often used to actually frame the data to create a data frame. So we often get a header and a footer on to the data, and the headers that are flowing down through the stack. One of the most common is Ethernet, which includes both a source and destination MAC address, which is like a physical address of a computer. Then at the bottom we have the physical layer, which is involved with bit level communications, the cables, the connectors, and so on. So we typically get copper cables, fiber, radio, and so on. As we go through connecting to internet devices, we might go through a partial stack. So we can see here in this case that the host on this side is connecting to a host on the other side. And as we go through an interconnected device, such as a router, it will go up through the layers, in this case up to the network layer. The router can then make a decision as to which port it will send it on to next, go through there, and then go back down through the stack again. Might be a different physical layer, different data link layer on the other side, and then onto the other side we go through the whole stacks again. In terms of a switch, we might only go up and down 2 layers, as we see here. And in terms of a proxy, we might go up 3 layers up to the transport layers. Some of the devices that we might see, often the internet model merges the higher level layers into what's called the application layer, because it's quite difficult to decouple these into the strict layers. So the internet model often defines these layers 6 to layers 5, 6 and 7 as the application layer. So our data itself can be encrypted to keep it secure using RSA, DES, 3DES, and we can involve some sort of hashing onto the data before it goes through the stack. At the application layer we have security protocols such as HTTPS, SSH, SFTP and so on, which build on secure sockets. At the transport layer we see this secure socket level, and we can also have the concept of proxy servers. At the network layer we can have firewalls, network address translation and interior routing protocols. At the data link layer we have the concept within security of VLANs, wireless web keys, 1x authentication, TKIP and wireless, PEEP and DHCP. And then at the physical layer we obviously get the physical protection of equipment such as padlocks, creating fiber cables to stop radiation from coming out and so on. So one of the most basic protocols that we will come across is ARP. And ARP is one of the most useful protocols in that it resolves the last little bit of an address. So as we've seen before, we have network addresses and we have data link addresses. So data link normally involves some sort of MAC address, some sort of physical address, such as a telephone number, and a network address is more like a logical address. To be able to transmit to an actual device, we need to match both its logical address and its MAC address. And it would be very difficult to actually find out what the MAC address was of any distant node. What we know is typically the logical address or the network address. So ARP is a protocol that allows us to find out what the MAC address is of a certain logical address. So in this case, this node here, Bob, wants to actually find out what the MAC address is of the gateway. Okay, so if Bob wants to get out onto the internet, he must actually find out what the MAC address is here to be able to communicate with this port, so that the router can actually send the data out onto the internet. So Bob sends an ARP request broadcast to the network, so every node on the network bounded with between routers will actually see this ARP broadcast. So this node will see it, and this port here will see it also. And it says who has 192.168.75.132. Okay, so over here, what we have is the broadcast. So in this case, the broadcast goes out, and who has that address? So let's say that that is .1 as an example to fit in with what it says here. And then over here, we'll make this .1. So Bob sends out a request to the network asking for 192.168.75.1, and then the router port here actually has that IP address. Okay, so that's .1, and then we'll broadcast back only to Bob, because we're using a switch here, what the MAC address is of this port. Bob then adds it to what's called his ARP cache, so he doesn't have to request it for another while, and then he's able to communicate with a destination IP address and with the MAC address of the router port. Okay, so here's an example. So in this case, we have a request, who has that address, and tell this node, gets sent out, and then the ARP reply comes back, and it says what the MAC address is of that IP address. Once that's complete, then the ARP table is actually updated with the mapping between the IP address and the MAC address. Unfortunately, we can get, in security, we get a concept called ARP spoofing, where a device can actually send an incorrect MAC address for a certain IP address, and thus possibly stream off the traffic onto another node. Okay, so here's an example of an ARP request. So we can see here that a node has requested this address, and we want to tell this node. Then we can see the reply coming back, which says where the address is. Okay, so this here is the broadcast address, which relates to this ARP request here. And here are some of the things inside the ARP packet, and it sits inside an Ethernet frame. So now we'll look in a bit more detail at the three basic protocols that are often used inside any internet communication, and that's Ethernet, IP and TCP. And they basically fit together like this. So as we've seen with our model, we take our data, we stick on some extra application data, we then add our transport data at the network layer, so this is where we get routers, and we add on our data link layer. So this normally involves framing the data into a data frame, and then that's actually sent over the network over some copper or fiber connection. So the three basic protocols are like this. This is Ethernet, IP and TCP. Okay, so normally we actually put our IP packet into here. Okay, so whatever comes down from the network layer is actually added into here. So Ethernet has some basic preamble at the start, ones and zeros, and then we have a destination MAC address, which is 6 bytes long, and a source MAC address. So this is the sender, and this is the recipient MAC address. The next thing defines what the basic type is of the payload of the Ethernet frame. If it's hex 800, then it's IP, an IP packet, such as this one. If it's hexadecimal 806, then it's an ARP packet. Okay, so in this case, if it's 800 hex, then we might get an IP packet header, such as this. We have the version number, the other key things, time to live. The actual protocol is important because the IP can carry most types of transport layer protocol. So in this case, it might be a TCP protocol for the transport layer, but it might also be ICMP, EGP, UDP, and so on. So the value that we see here actually determines what comes next. We'll have had to check some source and destination IP addresses. The IP header looks like this. As we'll see, we have what's called a source port and a destination port. These are things that applications connect to from one side to the another. TCP is a reliable protocol, so it uses sequence numbers to define each segment, and then we get acknowledgements from the other side to say that they've successfully received the data segments or not. And then we have the flags, which we'll see in a little while. A window size allows for a number of data segments to be sent at any given time. Then there's a very basic checksum. Okay, so this is what an Ethernet frame looks like. Okay, so we have basically the destination and the source MAC addresses, and here we can see that the payload in this case is an IP packet. A key thing to note is that the manufacturer ID of the network card is contained within the first 24 bits of the MAC address. We have 48 bits for a MAC address, and these first few characters, in this case this is the VMware adapter, actually identifies the manufacturer, and the rest of it should provide some unique ID. Okay, so let's have a look at a sample data packet, and we'll just look at a very simple web page access. Okay, so in this case we can see here there's the broadcast address, which is all F's, and that's part of an ARP request. And we can see here when we get a reply, it comes from one machine to another. Okay, so all of these involve some sort of communication encapsulated inside an Ethernet frame. So we see here that we just reopen this again. So we see here the type is 0806, which is ARP, and in this case it's an IP packet that's been contained. Okay, so how does this actually relate to the transmission of data from one computer to the next? So let's take an example. So this is a router here, and this is a switch, and here are our hosts. So this is the address of the sender, and this is the address of the recipient. So to be able to communicate, what happens first is that the host sends an ARP request to the whole of the network for this gateway port here. So the ARP reply comes back and it will identify what its MAC address actually is. So then an IP packet is now created with a source IP address of this and a destination IP address of this. Then a data frame is created with a source MAC address of this and a destination MAC address of this. So that data frame is then sent to the switch. The switch then forwards it on because it knows where all the MAC addresses are of its connected devices to here. The router then looks at the data packet and says it's destined for this network. So it looks at the network part and it says, I know the best way to get to that. I will then forward it on to this port here. It will keep the same source IP address and destination IP address, but now the MAC addresses will actually change. So this will become the source IP address, a MAC address, and this will become the destination MAC address for the Ethernet frame. Remember that the source and destination IP addresses will stay the exact same. So it then is able to get onto this port. This router here then examines the destination IP address and decides that it knows the best place to put the data frame next is here. In fact, it now knows that it's on the same network as it is. So it sends it over here. It keeps the same source and destination IP addresses, but now the MAC address will actually change for the source MAC address and for a destination MAC address. If it doesn't actually know what the MAC address is, it will obviously do an ARP request for this address and be able to resolve to this MAC address. Once it finds that, it will then be able to directly send the data frame and the data packet to this node. Okay, so we talk about at the data link data frames. At the network layer we talk about packets, IP packets and datagrams, and then at the transport layer we start to talk about segments. So let's look at a very important protocol, which is the IP protocol. And it's the IP protocol that really makes the internet work. So the IP header is made up with a version number. So this is typically either version 4 or IP version 6. So the version number determines what comes next. So in terms of IP4, which is the most common version of the IP protocol, this is the header. So we have the header length, type of service, total length, identification of the IP packet. We have a more flag, fragment offset that we'll see later. We have a time to live. The time to live, this value is decremented by each routing device that actually sees the data packet, and then when it becomes 0, then the data packet is deleted from the internet. So this stops data packets from traversing the internet indefinitely. As we've seen, the protocol defines what comes next, either TCP, UDP, and so on, and then there's a checksum. After this, we have the source and the destination IP addresses. So these are 32-bit addresses which define the source and destination addresses. Okay, so let's have a quick look at an example of the IP header. Okay, so there's our Ethernet, and then we have IP. Okay, so this is version 4. There's the header length. And we have an identification. So that's meant to show that the consecutive IP packets aren't the same. Then we have some flags. So there's the more for more fragments, don't fragment, and so on. There's a time to live value here. Header checksum. And there are our source and destination IP addresses. So you can see here, this is what our addresses looks like. So these are hexadecimal addresses. So let's see if we can calculate these. So hexadecimal C0 equates to 192, as we can see. A8 hopefully it should give us a 168, and it does. Okay, so we can see there's the hexadecimal format of the addresses, and they are contained in them. The structure of IP addresses is around a class format. So the first bit often identifies the actual class of the address. So it starts with a 0, then we have a class A address. If we have 1, 0 at the start, it's class B, and then a 1, 1, 0 is a class C. So in order for the internet to work, routers need to understand which part really relates to the network. So we segment the addresses up into a network part and a host part. Routers are not concerned with the host part at all. This is used to resolve the last part of the route. In terms of class A addresses, the first 8 bits, or these 7 bits here, identify the actual network, and all the rest of this can be then used for the host within inside that network. So it's possible to have 126 hosts because we're using 7 bits. All zeros and all ones are reserved, so we only get 126. And 2 to the power of 24 minus 2 gives us the actual total number of hosts that we can get on each of these class A addresses. The subnet mask is then used to define which part is the network part and which part is the host. So whenever we see ones, these are all ones, this identifies the network part, and wherever we see zeros, this identifies the host part. So class A addresses are typically used where we have very large networks with lots of hosts, but there obviously isn't a lot of these networks around. The class B uses the 16 bits here to provide the network part and the rest of it for the host. So in this case we have a 1 and a 0 here, so if we fill these all with zeros we would get a value of 128. If we then filled them all with ones up to a 0 here, we would get 192. So the address range is from 192.0.0.0 to 191.255.255.255.255. As we have 14 bits here, we can have 2 to the power of 14 minus 2 host networks, or about 16,384 networks that can be allocated, and we can have 2 to the power of 16 minus 2, or 65,534 hosts on each of these networks. Subnet mask in this case identifies that the first 2 parts are network and are significant for the routers. The second part is the host. Class C uses 1100. So if we filled these up with zeros, we'd actually find that would relate to a 128 plus 64, which is 192. And then we filled it up with all ones, we'd get up to 223. And that's the address range. So this time we can have lots of networks here, but we can only have 8 bits to identify the hosts. So we can have up to 254 hosts, which is 2 to the power of 8 minus 2. Two other addresses that we have are class D for multicast and class E, which are for research purposes. Another important concept inside the IP protocol is IP fragmentation. The IP packets themselves allow for up to about 64,000 bytes of data to be carried inside the IP packet. But unfortunately, the actual carrier of the data, normally the data link layer, is often limited with the maximum transmission unit that can be contained within it. So in the case of Ethernet, this is only 1500 bytes. ATM might only have about 64 bytes, and so on. So IP fragmentation takes the IP packet, if it's too big for this MTU, and then we'll fragment it up into IP fragments. So in this case, the more flag is set, and then we can define the offset, the fragment offset. So in this case, our RP packet is being fragmented up. So there's the length of 1000 bytes, which is then contained inside the Ethernet data frame. So it's below the MTU, so everything's fine. So then we have the next one, and there's the more. We have an offset of 1000. We have another length of 1000, and so on. So at the very end, the more flag is not set, and then there's an offset, and then we get the tail end of the IP packet at the end. So in this way, routers or devices can actually build up the original data packet back up into its original form, in this case into the larger IP packet. Unfortunately, intruders can use this to their advantage, and what they can actually do is to craft data fragments which overlap. So in this case, we can see here we have our first IP fragment, it's a length of 1000, but the second one is only offset by 400 as the same length, so it can confuse the device and crash the buffer by overlapping the data, such as in the teardrop attack, and it can also confuse devices in leaving a gap. So systems such as Snort, which was an intrusion detection system, and several servers actually were vulnerable to this type of attack, as they buffered the data segments continually and never building the data back up because there was actually a gap in the data. So this can cause buffers to overflow. The first transport layer protocol that we'll actually look at is UDP. And UDP is a very simple transport layer protocol, and it basically just has a source port and a destination port, each are 16 bits. So the connection, whether there is no connection, the data is sent, the client creates a unique UDP port and connects to a well-known UDP server port on the server. So the binding of the UDP port on the client and IP address and the UDP port on the server and its IP address are unique over the internet at that specific time. If the client needs to create a new connection from itself to the server, it will create a new UDP port for itself and connect to the same UDP server port. Not connect, but it will send the data to that port. So some well-known UDP protocols include DNS, DHCP, Trivial FTP, MSRPC, SMTP, and so on. So it's much faster than TCP as it's connectionless, but it has no sequence and acknowledgement numbers, so it's often easier to spoof. Okay, so this shows an example here. So UDP is contained within IP, which is contained within an Ethernet frame. Here is the destination port, 53 in this case, so this is DNS, and the source port that's used relates to what the client actually wants. There's the length, and then there is the checksum. Okay, so let's see if we can find an example. Okay, so there is UDP, and so this is port 53, there's the 53, 16 bits, 0035, and then there is the source port that we're using. Okay, so there's no connection involved, and this is using DNS. So it's a very simple, lightweight protocol. Okay, so now let's look at a connection-oriented protocol, which is TCP. With TCP, it's more complex. We have a 16-bit source port and a 16-bit destination port, but we also get the concept now of a sequence number for our data segments and some sort of acknowledgement. Along with this, we have a number of flags that we can actually use to identify the state of the data connection, of a window, checksum, and so on. So in this case, again, like UDP, but this time we create a connection. We have a TCP source port on the client, and we have a server port on the server that we connect to. If we create a new connection from the same host, then it will have a different client port but connect to the same server port. So well-known TCP transport layer protocol services include FTP on port 20 and 21, SSH, Telnet, SMTP, DNS, Finger, HTTP, POP3, MSRPC for remote connections, SSL, SMB over IP, and MSSQL. So the significance is that these are key ports for determining the services which are being run on the network. Often if we want to bar these services, then some firewall is then used to block any connections on that port. There is a key objective of locking down systems often, so we find that on servers we disable things that aren't actually needed, and that reduces the opportunity for intruders to attack the system. Some security issues with some of the protocols include FTP. Port 21 is used for the control and port 20 used for data. Unfortunately, it sends its data in clear text passwords, and the network sniffer can often find these user IDs and passwords, and often there is bad directory permissions where someone could log in with a low level of access and access directories within inside the system. Telnet uses plain text passwords, They aren't encrypted at all. So again, they could be sniffed by an intruder, and also once a user is logged in, they can perform virtually any action. SSH has now replaced Telnet in many systems, as that involves an encrypted form where the passwords are not sent in plain text. SMTP is an email service on port 25, where we have the email sent with an address header and also with the text itself and any associated documents in a single email message. In the past, it has been used for spoofed email and also has spamming problems. Often SMTP is actually blocked by domain firewalls. DNS, as we'll find in the following units, converts fully qualified domain names, such as Microsoft.com, into IP addresses. It trains an SOA, which describes the namespace, the zone namespace, an A record, which maps an IP address with inside the domain to a host name, such as www.microsoft.com would be a host with inside the Microsoft.com domain. NS defines the IP addresses of the name servers with inside the domain. MX defines the default mail servers. Unfortunately, it suffers from many problems, such as ARP cache poisoning, where fake records can be sent to clients which will change the IP address resolution of a fully qualified domain name. They can also suffer from denial of service attacks. They're a key element of the internet, and without them it'd be very difficult to operate. We can have TFTP, that is a simple FTP over UDP, and it's often used to transfer router and modem configurations. Unfortunately, it has no authentication and is often a target of attack for intruders. HTTP is a simple connectionless protocol used with web browsers. Unfortunately, it can be weak with browser scripts, such as with the Code Red virus. An SNMP is used to monitor networks. And we have the Simple Network Management Protocol, SNMP, which can monitor devices such as routers, so we can determine things like the number of data packets passing through, the temperature of the processor, and so on. Unfortunately, they use default passwords, which are easily guessed, and the text is often in clear text format. TCP is a connection-oriented system, and it uses the flags to determine the basic state of the connection. So one of the core flags is the SYN flag. The SYN flag is used to identify that a client wants to connect to a server. So in this case, a SYN flag is sent to the server. If the server acknowledges that it will accept the connection, it sends back a SYN-ACK, and then the final part is the client sends back to the server an ACK to acknowledge the connection. This is known as a three-way handshake and is the start of any TCP connection. So can you see here an example? So in this case, this is the client and it's connecting to a destination. So we can see that there is a SYN. The SYN flag is sent. The next thing, the client responds back to the server with a SYN-ACK on the FTP port, and at the end we see the client responding back with an ACK at the end of it. So let's see if we can have a look at this. Okay, so here's the three main steps at the start of the connection. So we can see here, then we have the SYN. Okay, so there's the SYN. The SYN here comes from the client to the server. Then we have a SYN-ACK, SYN and an ACK, and then we get an ACK at the end from the client, and we can see then we can then go into our connection. Along with this, we get the concept of sequence numbers. So the sequence number is the sequence that we've actually sent. It's the number of bytes. So we can see here the SYN is sent, sequence 0. The ACK comes back and identifies the next value it expects to see. So it's acknowledging everything up to that point. So in this case, the sequence number is 1, which matches the acknowledgement number here. The client also acknowledges that it's received the SYN-ACK in this case, because it says that it's expecting to see sequence number 1, which it does see next. The window size is negotiated, and that determines the number of data segments that can be received before the client has or the server have to wait for an acknowledgement to come back. Okay. So this shows a simple example. So we see the SYN, the SYN-ACK, and then the ACK there. At the end of the connection, we see a TCP shutdown. So a shutdown can happen either in a timeout or for a formal disconnection. So for this, when the client wants to finish, it sends a FIN-ACK to the server. The server then sends 2 TCP segments back, the first one with an ACK flag sent, second one with a FIN-ACK, and the client acknowledges all of that with an ACK. So we can see here, this shows the 3 sequences. So the first one is here. So the first one is here. So this shows a FIN-ACK from the client to the server. This one is the server responding back, in this case with an ACK. Then we see the server responding back again with a FIN-ACK. And then finally, the client acknowledges the whole teardown of the connection with an ACK. So in this way, the resources are then released from both sides. Another key protocol which we need to investigate is ICMP, which is often used in debugging purposes, but is often used also by external intruders to discover the network and its resources. So the ICMP packet looks like this. There is a 0 at the start, and then we get a type code followed by a code. So in most cases, the type is an echo reply or an echo request. We also have a destination reachable, source quench, and redirect. One of the most common replies that we get back is type 3, and type 3 we get a number of codes coming back, such as that the destination network is unreachable, host network is unreachable, the protocol unreachable, port, and so on. These messages can also can be used to determine whether something has been blocked by a firewall or whether a host actually does exist or not. So we can see here in this case the ICMP part is here, so it's carried within an IP packet, and we don't use TCP in this case. So what we do is we use ICMP. So the protocol part is determining that what comes next is ICMP. I can see in this case that it's an echo request or a type 8. In this case the code is a 0. Okay, so let's see a simple example of this. So in this case we are pinging from this computer to this one. So we send out an echo request type 8 and ping on a Windows machine the data packet looks a bit like this, and then a code type 0 comes back for the echo reply, and that says that the node actually exists. So let's look at an example for this one. Okay, so here we are. So there's the IP part, there's the Ethernet part, and there's our ICMP. So you can see here that it's a code type 8. It's a type 8 with a code 0, and there is a reply coming back. It's a ping reply. We can see the payload has got ABCD and so on. And we can see here there's the pings that we get. As a final thing, we'll have a look at the basic attacker process, which we'll build on in following units. That often involves 6 main steps that an intruder might go through, so each becoming a higher escalation. So there is normally some sort of reconnaissance outside, such as looking at DNS tables and IP information. And it's looking at generally publicly available information such as WHOIS databases. The intruder then might get more specific information about the network devices, the hosts and so on by scanning and enumerating devices, finding out where they are and what their addresses are. Then to gaining some access into a server or a device. After that, to find some weakness, such as cracking a password or breaching a firewall, and then on to some sort of escalation of privilege, where an intruder can move up through the levels. From there, they can then maintain access to steal data, do some damage or some user abuse, and then after that they might cover the tracks and place backdoors. Okay, so we've had a basic look at the OSI model. We've looked in depth at Ethernet, IP and TCP along with UDP. We investigated some of the TCP flags which are used inside our connections. We examined some of the ports that are used within TCP IP, and then we looked at ICMP. Okay, so this is the end of Unit 2.